Okay, in the first place, we will start with the mass spring damper system in order to estimate or to build the Kalman filter. Okay, and so we will add some random noise to the measurement and the process noise, and then we want to remove these noises from the measurement one. Okay, and so we start the mass spring damper system with noise. Okay, as always we do, we need to give the clear all, close all, and CLC, just like this one. First of all, we need to give the initial values. X0 is equals to the 0, V0 is equals to 0, because we have the two states in the mass spring damper system. We have 2 times 2 state matrices, in which the first of one is the watt, is the position, the other one is the velocity. Okay, so the M is assigned with the 1, C is assigned with the 2, and K is assigned with the 1. Okay, so for the numerical solution, we had title in here, numerical solution can be defined with the what, with these parameters. First of all, the dt is assigned to 0.01. This is the sampling rate of the R system. Especially for the watt, the STM or the other microprocessor, you need to select this because the Kalman filter is based on the watt, is run based on this period. Okay, and so its results or the conclusions or the performance depends entirely on these values. Okay, and then the initial and final time should be defined. TF is equals to 20, TI is equals to 0. Okay, and so the T is a vector just like this one, TI dt and TF minus dt, and we need to take the transpose of this value. And after that we need to give the how many points are utilized in the loop. Okay, and so the length of loop is assigned with the what, with the TF minus TI divided by dt. Okay, these are the how many points are contained in our algorithm, because we have the K in this is a discrete in this 0, 1, 2, blah blah blah, up to what, up to this length of the loop. Okay, so after that we need to give also the input signal, just like this one. F is equals to the what, the cosinus 2 times t. Okay, we can create these values just like this one, and so we have the 20,000 data to test our algorithm. So this is the basic parameters, and after that we need to design the Kalman filter design in here. Okay, so first of all, if we have any values with the S, we need to clear it. Okay, and so S is a structure with the values of the what, the 1 dt and K times dt divided by M, and so 1 dt times C M. Okay, and so how we can obtain this A matrix? Just remember that we have the M times X dot dot plus C times X dot plus Kx is equals to the F. In the discrete form, we can define as to the what, to this one. Z dot is equals to the bigger A times Z plus B times F, right? And so this is the state space form of these terms. But in order to discretize these values, and so the Z dot is assigned with the what? Z K plus 1 minus zk, and so divided by dt is equals to what, a times zk plus b times fk. Okay, and so if we reorganize the equations in here, z k plus 1, the velocity, and the what, position values, is contains what? 2 times 1 z vector in here, and so we can transmit the whole values in here, z k plus dt times a times z k plus dt times b times fk. Okay, and also we should write that k plus 1 is equals to the what? I plus dt, right? And times a, say, and times zk plus dt times b times fk. Okay. This is coming from this form of the equations form. Okay. So the result of this vector is assigned with the what? To this one. This A matrix is this one, I plus dt times A. Okay, it contains the dt values, k minus m minus c m, but also contains the what? The I values. Okay, so in order to do that, so we need to build this values in here, just like this one, and so we need to give or create the measurement noise variance. Okay, because the variance is the square form of the standard deviation values. Okay, and so it's the identical or the meaningful value to assign to the the measurement noise, mn std 0.004. okay, and so mn std times std. Okay, so this mnv değeri, v value is equals to what? It's based on the standard deviation. This is coming from the sensor data sheet. Maybe the minus plus values at measurement can be assigned these values. Okay, and also we need to define the process noise variance. Okay, pn std is equal to 0.002. This is the random values right now because we don't know anything about the physical system, but in your system you should assign some meaningful data for to do that. Okay, so after that we need to create the process covariance matrix in here. SQ is equals to the 0.0001 times I2, because we have two states, times P and V. Okay, this is the ratio of the the variance values. Okay, and after that we need to define the measurement function or matrix to return the state. For example, H can be assigned with the 1, 0 and 0, 1. Okay, and also C out must be defined. This is the output matrix, 1 and 0, 1. Okay, so in this case we estimate the both position and velocity, and also we obtain or measure to the position and the velocity in here. After that we need to define the S times R or measurement error matrix or coefficients, just like this one. SR is equals to the 0.01 times I2 times M and V. This 0.01 is arbitrary values for this process, because we don't know anything about which value is the best at this case. Otherwise we need to implement the adaptive approach in here. Okay, and also we need to give the SB function in here, 0 and dt divided by m. Okay, just like this one. So after that we need to give the initial states as x, x0 and v0 value. Okay, and SP covariance error matrix is initialized with the what 2 times m and v. Okay, and also as that p value determinant SP. This directly relates to the values of the trace. Okay, and so trace can be measured by using this term. If the determinant is going to the 0, and so we means that the diagonal element is going to 0 as well in here. And also as z, the observation values is initialized with the 0, 2, 1. Okay. So these are the Kalman system, and after that we need to simulate MCK system in vectors. For example, the true is a variable, the zeros length of loop in here with the 2 columns. Okay, because the true is a real dynamics, real ideal state values for the what, for the position and velocity in the vector notations. Okay, and so true TR is equals to what, the same idea is to what, the norm dynamics. This is the true dynamics. And also we need to define true noisy signals, the zeros. This is the noisy dynamics. This is the measured dynamic in the what, in our system. The physical system can be measured or obtained the position and velocity value from the what, from the noisy inputs. Okay, and so this is the measured signal values, and the true noisy out is the processed signal, noisy out dynamics. We can out everything by using these values, and also the true output, the ideal output signals in here. We have 5 variables in here, vector notations, and also we need to assign to what true 1 is equals to the what, x0 and v0. Okay, and that p1 is initialized with the what, s that p. So these are the case, and these are the Kalman filter, but the real system possess the other dynamics, system matrix, just like this one. ATR is equals to 1 dt and k times dt divided by m, and 1 dt times c divided by m, and BTR, the true dynamics, is given with what, 0 and dt divided by m. Okay, so how can we create the R solution? The forward difference solution can be given by the for I is equals to the 1 and length of loop minus 1. Okay, these are the basic forward difference conditions to what, beginning with the 0 to up to the length of the loop, and so the R solution, the time solution, is created at this line. Okay, and so first of all, at each case noise process should be defined, Pn std times rent n to 1. Okay, so at each case we create to the what, the different noises, and also noise measurement. Measurement is given by mn std values. It's the what is the variance of the measurement noise, and so we can generate the output. And so in the first place, true tr true tr I plus 1 and 2 states is assigned with what, atr times true tr I 2 states transpose plus b tr times fi. Okay, These are the true system dynamics without the noise. True system dynamic. This is the basic ideal case to compare the other results based on this information. And also we need to create the noisy dynamic in here, which is equals to the what? The true noisy is equals to the what? I plus 1 and ATR times true noisy I transpose BTR times FI plus noise process should be added in here in order to create the noisy output in here. And so the true noisy out should be defined with the what? With this term C out times true noisy states I plus 1, the next state, transpose plus noise measurement. Okay, and so we create noise process and noise measurement, and so we need to use this value because this value is our observation in here. Okay, so how about this? In this case, the Kalman dynamic can be defined with the what? This is the emulation of the whole of the system in here, because in the real life we have possessed this. We don't need to write in the real life application for this case, but in the Matlab application we need to write this dynamic because we don't have any physical content or the systems in here. But if we are using the what, these terms, and so we can create the what, the noisy process and noisy measurements in here, just like this one. And so the Kalman dynamics, the true I plus 1 is equals to what? S I in this is the structure A times true I and S I dot B times F I and plus noise process. Okay, and so S I Z values should be assigned S I times H. See that this H is the what are measured matrix, but it's contained in the Kalman dynamics, not the C out one, because the C out may contain the only position value, not the velocity, but this H is the estimation matrix in here times true I plus 1 and plus noise measurement, right? See, in the Kalman dynamics we add one more values in here, okay, because this is the noise output, and so this is the measured output, but we need to add the noise process and noise measurement in here. And after that, as I plus 1 should be find out the phi Kalman filter function with the argument of the structure of S and Fi. Okay, we need to write this phi Kalman filter implemented, and that p values I plus 1 should be assigned as I plus 1 right now, the determinant p. Okay, and so the true output of Kalman filter can be defined right now. True output is I plus 1 is equals to S I plus 1 dot X, because the internal state of X is the ideal output. X hat is given in here, just like this one. Okay, so how we can define the phi Kalman filters, and this is the main algorithm. Phi Kalman filter. Okay, so the function should be returned to the S phi Kalman filter, right? And so it takes the what, the S and U values in here and end. Okay, so from the equations, Sx is equals to what? S time dot A times Sx plus Sb times U. Okay, and Sp value is defined with what? The state transition matrix Sa times Sp times SA transpose plus S dot Q. Okay, and so the compute Kalman gain. Okay, and so the K is equals to what? SP times SH times inverse value S dot H times SP times SH plus S dot R. This is the equation of the Kalman gain. And after that, correction based on observation should be given in here. Sx is equals to Sx plus K times Sz minus Sh times Sx. Okay, the noisy output is feeding to the what? The internal state of the x hat values in here. Okay, and so after that the R ideal value is obtained in here, and so S dot P is assigned to what? S dot P minus K times SH times SP. Okay, these are the what? The 5 Kalman filter function. Okay, so after that we need to plot R values in here, just like this one. The figure, the plot T through RT1 and blue line and line white 2.0. Okay, and hold on, must be given in here, and also the true noisy out. This is the measurement coming from the physical systems. This is the green, and okay, and after that true output. This is the Kalman one. Okay, this is the K and Q. Okay, and so the legend should be given in here. The legend true noise or the actual measurement and the Kalman results is given in here. Okay, and so if I run this code and then see that in this case we have to this line, the Kalman X, I'm sorry, this is the true output. Okay, and so if I run this code and then see that this blue line is I'm sorry, this also be grid on, should be given in here, just like this one, and so okay, and so this blue line is the ideal MCK system response under the what? The cosine is 2 times t. Okay, so this is the ideal response, but we measure from the physical system to the what? The green line. See, this is the green line, but this green line from the Kalman is converted into the what? Into the black line. See that the whole the coefficients or the whole the values is to the what? Removed from the noises values in here. See, and so the Kalman filter does not approaching the ideal state because our measurement is broken too much in here. But if this is the case, the Kalman is the online estimator is run and removes the whole the what? The noisy parts. And so see that the Kalman is effectively runs on this algorithm just like this one in the online estimation. This too much noise is given in here. That's not good. But the Kalman, even if under this condition, Kalman generates to what? The ideal states for this one. For example, if I choose these values, and so what about this one? If I choose the S is equal to 0.1, and so if I run this code and then just see that the R algorithm does not change the values of the what? the Kalman filter response, because the process noise is applied on the what, on the R physical systems. And so if I choose the what, the Q is greater than this one, and so the Kalman permits to the Q matrix to the what to noise happens in here. And so if you want to remove the noises, we need to increase the values of these terms, just like this one. And so the noise level is what is smaller right now, and so if we increase the more zeros in here, just like this one, and then see that is closing to the what, the ideal response. But this is not the case in here, because if the Q is too much small or assigned to the 0, and so this is a false result, because if we assign the Q values is the 0, and the black line and blue line is on the what, on the same page. This is not the ideal case. This is wrong, okay? Because the R measurement is given in here, and then we have the some deflection in here. And so the process noise Q matrix must be greater than the 0 for the what, for the better results, okay? Because so we cannot have the ideal states in here. This is meaningful state for the Kalman. Otherwise, we cannot measure these values in here. And so, if we assign the Q as a 0, this is not a Kalman filter. This is the basis of the what, of the R emulation algorithm. Okay? And so, this the standard MCK values are generated in here. This is not a Kalman filter. Okay? But you may look the results and it seems the perfect, but our physical system does not behave like this, because we have the, for example, at the 14th seconds we have the measurements in here, and so our system is also going in here. This is the ideal, but the happening x values is around them, and so this result is wrong. Always we should select the Q matrix greater than the 0. Okay? And so this is a good result right now. For example, if I choose to what 0.1, and so the process noise does not deflect it in here. What about the effect of the R, the measurement noise? If we take into the smaller values of the R and see that we have no Kalman filter in here, okay? And so if I select the greater values of these terms, and so just see that we remove the some parts or the measurement error values in here. Or if we choose the 1 values in here, and then or 100 can be assigned in here, just like this one, and so the R signal closing to the what, to this point is the false area, because the R signal must on the what, on this line without a noise, right? And so if I choose the higher values in here, and then just see that our signal is going to what, the ideal MCK response, just like in the blue. This is wrong, okay? And so this is the optimization of the Kalman filter, okay? And so if we choose these values, this is not the ideal case. This is a wrong case for the Kalman filter, okay? And so the selection of the R and the other parameters are so important to obtain the real results of the Kalman, okay? So this may be equals to the what, and so this is a good results, and so we can choose the what, this one, and so this is an ideal case of the what, the R signals. See this term. For example, if your application contains the what that does not contain this kind of response, and so we can use this Kalman filter in here, okay? Because it's the ideal, and the noisy signal cannot be deflected by using this one, but we always steal to the what contains to continue to track the R noisy signal. Just remember that I said again, this blue line is the ideal case. But in the measurement, we don't have this kind of response. But if we are choosing the smaller Q values, and so this is not the ideal case. This is a wrong case for the Kalman filter, because we need to optimize the Q and R values. Okay, but in your application maybe it is consistent or the appropriate for your application, but otherwise maybe this one is good for your application. Okay, just remember that this is the Kalman filter implementation for the FOAT for the MCK signal. The blue line is the ideal line. We cannot reach this ideal line because the R physical system does not respond just like this blue line. But in the Kalman filter, if the measurement is given in here just like this one, and so we can track all the signals without what the measurement noise is in here. Okay, and so you need to choose to what the Q and R values based on these informations. Okay, so what about this one? The Cout is the R measurement matrix implementation. See that? This is the Cout. So true noise out is utilized in this one, in this domain. But if we assign the Cout, for example, the 0, which means that we don't have any position data on our signal, how Kalman filter behave like this? So from the velocity measurement, we estimate this one, the position values in here. And so if I run this code, and then the R code is estimated to the position values, just like this one. See, the position values is estimated in here, or we can estimate to to velocity values in here, just like this one. And so the position is to is assigned with the one variable, the position measured, but the Cout not measured in here. Okay, and so if I choose the 0 and 0 values, and so the R Kalman filter behave like this one. But this is not the case, because we can iterate the R stem, emulate the R Kalman filter in here, but this may be meaningful or not in here. This is the sensorless application for the R algorithms. Okay, so this is the case for for our algorithm to select the Kalman filter implementations in here. But we can utilize another algorithms in here, just like this one. The Cout can be assigned just like the true noise output. And so if I choose the 0 values in here, the R response change. And so if I choose the 1 and 0 values for the position values, and so see that the R signal is behave like this one, right? This is the Kalman filter implementation of the R signals, because we don't have any position values in here. And so what happens if I choose this value, and so S and Q must be changed with this one or smaller than this one. Okay, see, this is the ideal case because we don't have the position values just right now, but we can estimate anyway by using these values, because we have the velocity values in here. But this Kalman filter output does not contain any noise signal, because we don't have any position measurement from the real system, noisy system right now. Okay, so but in the ideal case we should give this H true values just like this one. Okay, that's all for this lesson. In the next lesson we will talk about the van der Pol equation in order to implement the extended Kalman filter design. Okay.